right, so this is going to start our sections on growth modeling. um, Used to be that this was in two different sections, and now they've condensed it into one in the new book. So the whole thing is going to be found under 9.4 um, in the Calculus 2 course. If this is for my ABBC course, then you're actually going to find it in still two separate sections, 9.4 and 9.5. Either way, 9.4 is exponential growth and decay. It's actually a 2-day lesson, so it's going to be multiple videos here, two different sections. All right. So what we're going to see here is that because these are modeling questions, they're going to be application based. One of the biggest things is obviously understanding what the problem is asking you to do. You will find that through most of this section, it's going to be relatively repetitive as far as what you actually do process-wise. It's just going to be understanding how to get there. All right, so we're going to solve differential equation application-based problems here. The first one says the population of the little town of Scorpion Gulch is now 1,000 people. The population is presently growing at about 5% per year. Write a differential equation that expresses this fact. Solve it and find an equation that expresses population as a function of time. So there's a lot of stuff going on there. So we kind of need to go back and analyze what it is that they're giving us. Keep in mind that some of the information in here is probably a little fictitious. Scorpion Gulch, I do not believe is an actual place, although I could be wrong. And if it is someplace, I would probably guess it to be in, I don't know, New Mexico, Arizona, something like that. Just, Scorpion just sounds like that's where it would be. Anyway, says the population is now 1,000 people. That tells you that's some kind of an initial population or current population. The population is presently growing at 5% per year. Tells you some kind of a growth rate. And then we want to write the differential equation that expresses this fact. Remember, a differential or derivative is a rate of change. So we're given some information there that we can do that. Solve it and find the equation that expresses population as a function of time. So we basically want to write the differential equation that we can then solve for an actual population equation, not a derivative equation. So they're telling us that P is the number of people and T is the years after the present time, I guess. So let's start off with the differential equation portion. Well, we know that the population is changing. So there's a dP with respect to time over dt. And they are telling us that it is changing at a rate of 5% per year, which is 0.05. But here's the thing. It's not t. Okay, what is actually changing? If this was the actual population equation, then it would be population equals some function of t. But they're telling us it's the differential equation. So what is actually changing? The thing that is actually changing is the population. 5% of the population. That's what's changing. So this is going to be a P on the right-hand side. So that's the differential equation. Again, you'll get used to this as we go through it. If we want to solve this, this is now a separable differential equation. We can multiply the dt to the right, divide the p to the left, and we're good to go. So let's do that. We're going to multiply the dt. So we're going to get dp equals 0.05p dt. But we need to get that p from the right to the left, so we're going to divide both sides by p. 1 over p dp equals 0.05 dt. Technically, we could have taken the 0.05 with the p. I find it easier just to leave the constant values on the right, so we're only dealing with the variable on the left, if possible. Not always possible. It is separated. We can now take the antiderivatives or integrate both sides so that we have to use the antiderivative technique. On the left-hand side, we know that we get the natural log of the absolute value of p. On the right-hand side, there's no t's in it, so it's just going to be 0.05 t plus c. And then to solve that for p, we're going to exponentiate. Take e to be the base of both sides. e to the natural log of absolute value of p is just going to give us p. E to the 0.05 t plus c can be simplified as we've done in the past sections. Remember that that can be split up to e to the 0.05 t times e to the c, but e to the c is another constant. So ultimately what we get is the population equals that constant e to the c times e to the 0.05 t. That's a population equation in terms of t. And then obviously if we knew what c was, we would have the specific population equation, and that's going to happen in the next part. And a lot of you may actually recognize this general equation. If you eliminate the p equals on the left-hand side, you get that c e to the 0.05 t. Most people are probably used to that as being some kind of p e to the rt. The PERT equation, a lot of people call it, just because that's what it looks like it spells. That's the same exponential growth and decay equation that we're using here. And we just developed it by taking antiderivatives. So let's use the fact that the population of the town equals 1,000 at time t equals 0 to find c. We're given the initial conditions. Time t equals 0, we'll plug 0 in for t. We'll plug in 1,000 for the population and solve for c. So we would get 1,000, that's the population, equals c. E raised to the 0.05 times 0 is e to the 0. Again, remember that that's 1. So we get that c equals 1,000. So now we can just substitute it back in, and our population equation becomes 1,000 e to the 0.05 t. That is a horrible 5. There we go. All right, so I think that hopefully that that makes some sense. This process, this general idea is going to repeat as far as separating the variables and being able to solve the differential equation. Number 2. You run over a nail as the air leaks out of your tire. The rate of change of air pressure inside the tire is directly proportional to that pressure. Write a differential equation that states this fact. Evaluate the proportionality constant if the pressure was 35 psi and decreasing at 0.28 psi per minute at time 0. Solve the differential equation. All right, everybody got it? Let's go. No, I'm just kidding. Most of the time, you're going to have to read these things multiple times. There's a lot of stuff going on in this problem. We ran over a nail. Okay, bad us. As the air leaks out of your tire, the rate of change of air pressure inside the tire is directly proportional. Okay, that's a key. We're going to have to talk about that, to that pressure. Write the differential equation that states that fact. Okay, we'll get to that. And then we want to evaluate what that proportionality constant is if we're given some initial conditions, which we are given there, and then we'll solve the differential equation. So we got a bunch of stuff going on here. First of all, a direct proportionality is a proportionality constant. If something increases, the other thing also increases, and there's some kind of a constant that tells you what that is. That's called the proportionality constant. We typically use the variable lowercase k for that. So we know we want to write a differential equation. What is changing over what is it changing? So the pressure is the thing that's changing. So there's a dP, pounds per square inch, and the time is what it is changing. So dt. That is going to be directly proportional to the pressure. So the direct proportionality constant is K. P is the pressure. Now, if this was, and we're not going to go into this heavily, but if this was an indirect proportionality, then it would be a division, because that means as one thing goes up, the other one would go down. So it would actually be P over K instead of K times P. All right. We are given some information that's going to help us to find K. We need to find that proportionality constant. So they tell us that the air pressure is changing at 0.28 psi per minute. That's a rate of change. That's your dP over dt. Specifically, this is happening at one specific time at time 0, and they tell us that the pressure was actually 35 at that time. So we know that 35 is going to go in for the pressure, K times 35. And at that particular time, it is changing at 0.28. And it says that it is decreasing, so we're actually going to make that negative 0.28. So we need to solve for K. We'll divide both sides by 35. We get negative 0.28 over 35. I do realize most of you all are probably going to just use your calculator to simplify that. You can do it without. You realize that 28 and 35, ignoring the decimal for now, 7 goes into both, so it can be reduced. So we can actually divide both the top and the bottom by 7, which would give us negative 0.04 divided by 5. Again, this is only if you had to do this without a calculator. Then you could multiply both things on the top and the bottom by 100 to get rid of your decimal. So then you would get negative 4 over 500. And 4 does go into 500 125 times. So that would be negative 1 over 125 equals K. As a decimal, that actually works out to be pretty nice. I think off the top of my head, it's like negative 0.008 or something like that. I'm not using it, so it doesn't matter what the decimal is. So now we have that dP over dt is going to equal 1 over 125 p. And now we're in a position that we can go ahead and solve this thing, separating the variables. Multiply dt to the right, divide by p. Should look something like that. We can now integrate. And we should be back to what we kind of had in the previous page, the natural log of the absolute value of p equals 1 over 125 t plus c. So then solving that, we're going to exponentiate. And we now get p equals e to the 1 over 125t plus c. So that's going to be e to the c, which again is just another constant. E to the 1 over 125 t. In the part right below this, it says use our initial conditions to actually find c. So we are told, what are our initial conditions here? Initially, the pressure was 35 psi, so that's going to go in for p. And of course, that says initially, so that's at time 0. So we put 0 in for t. So we know down here, using this equation, that 35 was the initial pressure. At the initial time of 0 would give us e to the 0, and e to the 0 is 1, so we know that c is 35, which means that our equation is p equals 35 e to the 1 over 125 t. Okay, if you haven't already figured it out, that c value is going to be your initial value. So if you're ever given the initial condition, you don't really have to go through this whole process. When it comes to these exponential growth and decay problems, you can just pretty much figure out, okay, well, C is my initial condition, plug it in. We don't have to go through this portion to solve for C. There are other cases where that doesn't always work, but that's not your typical exponential growth and decay model. All right, so number 3. Bacteria in a lab culture grows in such a way that the instantaneous rate of bacteria is directly proportional to the number of bacteria present. Write a differential equation that expresses the relationship, separate the variables, and integrate the equation, solving for the number of bacteria as a function of time. Same exact idea. Let's change colors here. So we know that bacteria, or the number of bacteria, is changing over time. Okay? And so we know it says that it is directly proportional, so that would be K times the number of bacteria. Divide the B, multiply by dt, 1 over B dB equals K dt. Again, this is going to get repetitive. You're going to see the pattern. It's pretty much the same. And when we take the antiderivatives, natural log absolute value of b will then equal kt plus c. And then we will exponentiate. And therefore b will equal c e to the kt. Again, this should all look very, very familiar. All right, part B. Suppose that initially there were 5 million bacteria. 3 hours later, the number has grown to 7 million. Write the particular equation that expresses this number of millions of bacteria as a function of time. So, one of the things we need to do first here is we need to solve for K. We've got to solve for that proportionality constant. Okay, that wasn't just given to us here. So let's solve for the proportionality constant. Bacteria, the number of bacteria is B, but also C is the initial amount of bacteria. Again, we don't have to solve for that. We now know that that's what that is. So it says initially there are 5 million bacteria. So the 5 goes in for the C. We're going to need to solve for K. And we know that 7 million is the current number of bacteria. So in order to solve for K, we actually still need to know T. But again, we know that this says it is 3 hours later that it has grown to this. So actually what T is 3. Okay, so now we have everything we need to do to solve this. So we're going to solve it exactly as opposed to using a decimal approximation, because it'll actually be better, because the more you truncate and round your decimal early, the harder the problems will become later, the less accurate too. So we're going to divide both sides by 5. Now the k is in the exponent of the exponential, which means in order to get that out of there, we need to take the natural log of both sides. Again, we're using the inverse operations to do this. So we will take the natural log of 7/5 and set that equal to the natural log of e to the 3k. The natural log of 7/5 is just the natural log of 7/5. The natural log of e to the 3k, again, natural log and e are inverse operations, which leaves you with the argument, so that's just 3k. And then to solve for k, we divide both sides by 3. You can write the natural log of 7/5 all over 3. It's cleaner if you make it as a reciprocal. Instead of dividing by 3, you'll multiply it by 1/3. It keeps everything horizontally multiplied, as opposed to being some vertical mess of a fraction over kind of a fraction type of thing. So there's your k value. And then for b, it's going to equal 5. That was your initial condition. E raised to the 1/3 natural log of 7/5 all times, oops, not k, times t. And there we have our equation. The rest of this is using that equation. When will the bacteria population, what will the bacteria population be 1 full day after the first measurement? Well, everything was measured in hours before, because up here it said 3 hours. So we're going to keep it consistent. So we're talking about 1 full day, which is 24 hours. So we are really just trying to find b of 24. Okay, so that's just plugging in 24. 5e to the 1/3 natural log of 7/5 times 24. All right, now you could try and simplify a lot of this by hand, but again, because you're using the e part, unless it worked out to be an exact whole number, which some of them do, but most of them don't, this one you're just going to plug into your calculator. And when you do, you should end up with 73.789. And that will be, what is this, in million bacteria. Whew, a lot of bacteria. All right, last step. And by the way, I'm assuming that you all can plug these things into your calculator. make sure that you are at least practicing as we go along with this, plugging this in your calculator and you get this value. If you don't, you need to figure out what it is syntax-wise that you're not typing into the calculator correctly. Make sure you can do that. All right, part D. When will the population reach 1 billion, which is 1,000 million? So now they're asking for when. That means we're solving for T. They're giving us the new population, which is 1,000 million. That goes in for B. And then we have to solve this equation for T. So we're actually going to go through how to solve this by hand until we've solved the actual equation for T in terms of natural logs and all that kind of other stuff. And then we'll plug it into the calculator. Unless you know how to find the intersection or plug all this stuff in your calculator as it is, which is perfectly fine. If you know how to do that at this point, go ahead and do so. To solve this for T, we need to get the T isolated in the exponent, meaning we have to get everything else away from the exponential. Let's divide by 5 on both sides, which will give us 200 equals e to the 1/3 natural log of 7/5 all times t. We are then, I'm going to take a little shortcut here, we are going to then take the natural log of both sides, which will then give us the natural log of 200. The natural log is the inverse of e, so that gets rid of everything on the base there and just leaves us with the exponent, which is 1/3 natural log of 7/5 times t. And then to solve for t, we'll divide by 1/3 natural log of 7/5, which will give us natural log of 200 divided by 1/3 the natural log of 7/5. I am not worried about leaving the 1/3 in the denominator because we are going to divide by that whole thing. Once again, please make sure you know how to plug that in your calculator. And you should end up with 47.240 hours. If I haven't said so in the past videos, I'm using the 3 decimals for all of my stuff here because that is the way it is done for AP testing. So I've continued that kind of accuracy for everything. All right. There's still a couple more problems left to go here. We'll come back with a second video for this part because this section is running long. But just a little food for thought here. If this is really how bacteria grows, just think about what happened there. You started off with, what did we start off with? 5 million bacteria. Okay. By the end, or basically end of 2 days, 47 hours, almost 2 days, we are now up to 1 billion or 1,000 million bacteria. Bacteria grows and it spreads very, very fast. Very fast. So if you ever wonder why people get sick and things happen so quickly as far as how things pass on with bacteria, that's why. It grows very, very fast. All right, we'll come back with a second video and finish up this section. Again, this is a long section. Then we'll have a couple of videos for day 2, and then we will also do 9.5 in this section as well.